The first application of algebraic function fields we consider will be the algebraic coding theory. But before explaining how we can apply the notions from the algebraic function fields, in this lecture, I want to give a crash course on algebraic coding theory. The main concern is to transmit data successfully through, roughly speaking, through a noisy channel. And if possible, we want to detect or correct the errors in the corrupted messages. And if you see in algebraic coding theory course, the toy example, the first toy example, and my example will be kind of silly, but if you want to transmit a picture through a satellite, for instance, if we want to use the 4 colors, green, blue, red, and yellow, first we encode them. Actually, we will represent them as bits or elements of the two-dimensional vector space over the binary field. And for instance, if you want to send a color blue through a channel, and if our message is corrupted, and by the corruption we mean that, for instance, the second bit has changed, and if we received the vector 1, 1, the receiver think that the color was sent was yellow, but this is not the case. And one of the solution is the simple solution is to expand the length of these vectors. So in some sense, here we do encoding. And in this case, for instance, we can extend it as a sum of the first 2 coordinates. And exactly, we will have the same number of data. But in this case, for instance, if we received a vector 1, 0, 0, we will understand that, okay, something is wrong, but it can be possibly come from 0 vector. So it can be possibly green or blue or sorry, I think this is going to be 0 because 1 plus 1 is 0 in binary field. It can be possibly yellow. So at least, okay, we understand there's something wrong, but how we can correct the message. Mainly, our main concern is do we have a reliable communication? And the first important answer was given by Shannon in 1948, and in his breakthrough work, A Mathematical Theory of Communication, which claims that the reliable communication, whatever that means, and under certain condition is possible, but his proof is based on some probabilistic methods, and it doesn't give some constructive structures. And this is why researchers start interested in what kind of construction we can consider, like in this toy example. And this is why one of the most useful structure will be the vector spaces over finite fields. In other words, from now on, we will consider the finite fields as base fields. And we will consider the n-dimensional vector space over the given finite field FQ. And to be able to measure how far we are from the correct message, we endowed this vector space structure with a metric. Actually, with a discrete metric, which is defined as the number of the different components of the vectors A and B. And by the metric, what we want to mean is that it satisfies the four property of the discrete metric. So first one says that it's going to be positive and it can be at most n. And if the distance between two vectors A and B is 0, they are supposed to be equal. And this behaves symmetric. And finally, it also satisfies the triangle inequality. So the distance between the vectors A and C is less than or equal to distance between A and B and the distance between B and C. And indeed, we can easily check that this metric, which is also called the Hamming metric, satisfies this four property. And another closely related relation is the weight of an vector A, and it is defined as its distance to zero vector, or this is a number which counts the non-zero coordinates of the vector A. This is going to be Hamming weight of the vector A. And our main structure will be the subspaces of Fq to the n regarding the Hamming metric we defined here. That means a linear code C over the finite field, given finite field Fq is a subspace, is a vector space of Fq to the n. And we will call the elements of C code words. And we call n the length of our linear code C, and its vector space dimension over Fq will be denoted by, in general, with lowercase k. And if this is the case, we can briefly represent, parameters nkd, or we can briefly represent our code with these parameters nk and q. And if we also know its minimum distance, which is defined as the minimum of the distance between all code words, distinct code words from C. Of course, in this case, we suppose that C is a trivial vector space. Or equivalently, since we have a vector space structure, we can also define the minimum distance of a code word as the minimum of the weights of each non-zero code word. And in this case, we will represent our code with its parameters n, k, and d. In the literature, you may also come across some codes. I mean, we may also define codes as some substructures of A to the N. Here, A is not supposed to be finite field. It can be non-zero finite set or some local ring, or there are several examples. But here, our main concern will be the linear codes over finite fields. And thanks to these parameters, okay, we mentioned that D is kind of the measure, and what we can do with this parameter, and in that we can see that a code with minimum distance D is exactly a D-1 error detecting code. So that means a code C is T error detecting if and only if its minimum distance is bigger than T plus 1. And to see that, first let me show the sufficient condition. So let me suppose that the minimum distance of a linear code is bigger than or equal to T plus 1 for some integer, positive integer T. And if a code word C was sent, and if we received a vector X such that their distance is less than or equal to, strictly less than less than or equal to T. In this case, by the assumption, this is strictly less than the minimum distance of C. Then in this case, by the definition of the minimum distance, we can conclude that indeed this vector X cannot be code word in C, and in some sense we can detect some corruptions until until T-mini corruptions. So C is T error detecting code. And to see the necessary condition, let me prove it by contradiction. So let me suppose that minimum distance of C is strictly less than T plus 1, or equivalently, it is less than or equal to T. Then in this case, we know that there exist two code words and their minimum distance is exactly T. So that means if we send, in other words, if we send the code word C1, if we received C2, there is no way, this is still code word, and there is no way to detect an error. So that means C is not T error detecting code. And similarly, we can also talk about the correction by using the minimum distance. So in this case, we will see that a code word, a linear code C with distance D, is an exactly the floor function of the D-1/2 error correcting code. So a code C. By the way, by the code, we always mean the linear code. I'm not going to write it always. I'm not going to mention the linearity always. And is code C is a T error correcting code if and only if its minimum distance is bigger than or equal to 2t plus 1. And you can prove it particularly using the triangle inequality of the Hamming metric.